Tonight, we're going to travel to the edge of the universe, a boundary we can only see because we happen to be alive at the right moment in cosmic history. 46.5 billion light years in every direction. That's the room we live in. Most people picture the universe as a globe, a finite ball of stars and galaxies floating in the dark, with a definable surface, an inside and an outside. That image is comforting because it's the kind of object the human mind was built to understand. But the universe isn't a globe. The edge isn't a wall you could touch. It's something far stranger, a horizon made of time, not of space. By the end of tonight, you're going to understand why the edge of the cosmos is closer and farther than you thought at the same time, why the light reaching your eyes from the most distant galaxies is older than every story humans have ever told, and why we are, right now, living inside the single brightest moment in the entire history of cosmic time, a window that is very slowly beginning to close. Before we dive in, if you love exploring the cosmos as much as we do, take a second to like the video or subscribe and tell me where you're listening from and what time it is. I read every comment. Now dim the lights, let your shoulders drop, loosen your jaw, take one slow breath in and let it out. Let's begin. To understand a journey, you have to begin in the room where the journey starts. So begin in your room. Feel the chair or the bed beneath you. Feel the slight weight of the air against your skin, the temperature of the space you are in, the soft hum of whatever appliance is running in the next room. This is where you are. This is your starting point. From here, the universe extends in every direction, and in every direction the answer is the same. It does not end. It simply becomes more and more impossible to see. Most of us, when we picture the universe, picture something like a globe, a finite ball of stars and galaxies floating in the dark, with a definable surface, a definable size, an inside and an outside. That image is comforting because it is the kind of object the human mind was built to understand. We evolved on a small, round world. We learned to imagine other small, round worlds. So we project that shape outward, and we imagine the universe as a larger version of the same. But the universe is not a globe. The universe is not even an object in the way the word object usually means. It is a geometry. It is a stretching of space and time itself, a fabric that has been pulling itself apart for almost 14 billion years. And the edge we are going to travel to is not a surface you could touch or a wall you could stand against. The edge is a kind of horizon, in the same way that the horizon of the ocean is not a wall, but simply the place where your eyes can no longer follow the curve of the water. The horizon of the universe is the place where time can no longer carry light from there to here. That is what we mean by edge. That is the destination of this journey. Before you can travel to it, though, you have to understand what scale you are about to enter. And to understand that, you have to begin small. You have to begin with your own breath. A single breath of yours contains, very roughly, 25 sextillion molecules of air. That number is so large that the human nervous system simply rounds it down to a lot. 25 sextillion is a 25 followed by 21 zeros. Each of those molecules has been bouncing around the planet for hundreds of millions of years. Some of them have passed through the lungs of dinosaurs. Some of them have ridden in the wind across continents that no longer exist. They are old, your molecules. Older than the family that raised you. Older than the species that produced you. Some of them are older than complex life itself. Now exhale and let those molecules go back into the room. Already, you have done something remarkable. You have moved an enormous number of ancient particles by a tiny distance using almost no energy. That is, in some sense, the smallest unit of cosmic motion we will discuss tonight. The breath, the displacement of matter by a hand's width. From here, every other distance will be larger. Every other displacement will be greater. And by the end, the breath in your lungs will seem like the most local, most intimate event possible. A quiet stirring in the foam of one wave, on the surface of one ocean, on one shore of one continent, on one planet, in one solar system, in one galaxy, in one cluster, in one supercluster, in one filament of the largest structure that has ever existed. The first thing you should know is that the universe has a measured size, and that size is not what most people think it is. If you were to ask a careful astronomer how large the observable universe is, meaning the part we can in principle see, they would not say 13.8 billion light-years. They would say something close to 46.5 billion light-years in every direction from here. That number is strange because it seems to violate the rules. Light has only had 13.8 billion years to travel since the beginning. So, how can the most distant things we see be 46 billion light-years away? The answer, and this is the answer the entire script will rest on, is that space itself has been stretching during the journey. While the photons were traveling toward us, the distance between their starting point and us was growing. By the time their light arrives, the place those photons came from has been swept much, much farther away than it was when they left. So the photons we are seeing are old, and they come from a place that has, in a sense, retreated from us as we waited for them. The thing we are looking at is not where it was. The light is a letter from a sender who has moved. That image, a letter from a sender who has moved, will return many times before the journey ends. So already, you can feel the strangeness of where we are headed. The edge is 46 billion light-years away in the present, and yet the light from the edge has only been traveling for 13 billion years. The space behind that light has been quietly inflating and continues to inflate, and the inflation is accelerating. We will return to that acceleration. It is the deadline written into the geometry of the cosmos. For now, accept the size. 46.5 billion light-years in every direction. A sphere of observable space that, if you tried to measure it across, would be roughly 93 billion light-years from one side to the other. That is the room we live in. That is the scale of the journey. There is a temptation when numbers like these arrive to skip past them, to register the digits, nod at their bigness, and continue. Resist that temptation tonight. Stay with this number, 93 billion light-years across. A light-year is the distance light travels in 1 year. Light travels at 300,000 kilometers per second. In a single second, a beam of light can wrap around the Earth more than 7 times. In a single second. Now imagine that beam of light running for a year, then for 13 billion years. Then ask, how far is that, when even a year of it would already trace a path longer than every road and rail and shipping lane and migration route ever drawn by a living thing on Earth, multiplied by numbers we have no language for? The answer is that even a single light year is, in human terms, an unfathomable distance. And the universe is 93 billion of them across. This is the room we are about to walk through. The journey will be spatial. We will move outward, layer by layer, from your skin to the cosmic horizon. We will not skip layers. We will not jump cuts. Each layer has its own character, its own residence, its own kinds of silence. Each layer is, for someone, a home. And at each layer, you will be asked the same quiet question. What does it mean that this place exists, and that you are connected to it by nothing but a thin chain of physical law? Before we leave the surface of the Earth, there are 3 concepts you need to carry with you. They will be your provisions for the trip. The first is the speed of light, which we have already begun to feel. The second is redshift. The third is the cosmic horizon itself. Take a moment with each. Light, the fastest thing in the universe, is also the slowest courier the universe has. That sentence sounds like a contradiction, and it is the most important contradiction in cosmology. Light, in human terms, is impossibly fast. A laser pulse from your hand could reach the moon in roughly a second and a quarter. It could reach Mars, when Mars is nearby, in about 3 minutes. It could reach the Sun in 8 minutes and 20 seconds. And yet, on the scale of the universe, light is so slow that it can spend 13 billion years traveling and still not catch up to all the places that exist. The reason is that the universe is so large that even the fastest possible signal takes geological epochs to cross even one of its smaller corners. Light is fast in the kitchen. Light is fast in a solar system. Light is, on the scale of the cosmos, almost embarrassingly slow. That mismatch, the speed of the messenger versus the size of the room, is why we see only the past, never the present, of any place we look at. Redshift is the second concept. When something moves away from you and emits light, that light gets stretched. The waves arrive longer than they were sent. Long wavelength light is red. So we say the light has been redshifted. The faster something moves away, the redder its light becomes. Now imagine that something is not moving through space, but is sitting still, while the space between it and you stretches like dough. The light still gets longer. The redshift still happens. This is how cosmologists measure the expansion of the universe. They take the light from distant galaxies. They measure how much it has been stretched on its way to us. And from that, they deduce how much the space between has grown during the journey. Some galaxies have light so stretched that what began as ultraviolet starlight arrives as deep infrared whispers. Those galaxies are, for that reason, very far away. They have been waiting for us, in a sense, for nearly the entire age of the cosmos, while their light slowly red-bled across the gap. The cosmic horizon is the third concept. The horizon is the distance beyond which light from the universe has not yet had time to reach us. There are actually several horizons astronomers talk about. The particle horizon, the event horizon, the Hubble sphere, and we will meet them in turn. For now, hold a single image. The horizon is the edge of what is, in principle, visible. Beyond it, things may exist, almost certainly do exist. But the photons from those things have not been traveling long enough or fast enough to reach us yet. They are still en route. Some of them will never arrive. The horizon, in other words, is not a wall in space. It is a wall in time. It is where the deadline of light meets the patience of distance. These 3 things, speed, redshift, horizon, are your provisions. Carry them. They will return. Now look up. Even if the ceiling is above you, look up in your mind. Above the ceiling is the roof of your house, then the open sky, then the thin shell of the atmosphere, then the airless dark of low Earth orbit, then the moon, then the planets, then everything else. We will start there, with the air above your head. Because before we leave the planet, you should understand the shape of the planet itself. and the way that shape is so small in cosmic terms that the entire human species has barely climbed to its edge. You are sitting on a sphere of rock and metal, a little under 13,000 kilometers across. From your perspective, walking, the Earth is essentially infinite. From the perspective of light, it is something light can cross in a fraction of a second. From the perspective of the universe, it is a grain, a round, blue speck in a sea of black. The first checkpoint of our spatial spine. Above the Earth, there is the atmosphere, which thins so quickly that by the time you are at the cruising altitude of a passenger jet, you are already above 3/4 of the air. By the time you are at the edge of the stratosphere, you are above 99%. By the time you are at the boundary called the Kármán line, a little over 100 kilometers up, you are essentially in space. There is still a thin breath of atmosphere there, but for practical purposes, you are above the planet's gas and inside the local vacuum. That number, 100 kilometers, is the first measurement that should astonish you. The entire envelope of breathable, livable, sky blue, cloud-filled, weather-bearing atmosphere of Earth is a layer thinner than the distance between many neighboring cities. If you could drive straight up, you would be in space in an hour. The reason humans cannot drive straight up is gravity, and the engineering required to escape gravity is profoundly difficult, but the distance itself is small. We are bottled in by physics, not by space. That is the strangeness of our position. We sit at the bottom of a thin shell, gazing up at a universe that is 46 billion light-years deep, and the only thing keeping us at the bottom of the shell is the rule that says it costs energy to climb. We have spent the entire history of our species inside this shell. We have walked across it, sailed across it, flown across it, killed each other across it, written poetry about it. And only in the last 60 years or so have a few of us, a few hundred people total in the entire history of the human family, climbed even 100 kilometers above its floor. Hold that for a moment. The total distance any human being has ever traveled from the surface of the Earth, with very few exceptions, is less than the distance between two large cities on the same continent. The exceptions are the 24 Apollo astronauts who went to the moon between 1968 and 1972, 12 of them walking on its surface, and the 4 Artemis II astronauts who, in April 2026, became the first humans in over half a century to fly beyond low Earth orbit, looping around the moon and reaching the farthest distance from Earth ever attained by humans. Even those distances are, on the scale of the journey we are about to take, a step, a small step, the first step, almost nothing. Yet for now, we are not even at that first step. We are still in your room. The journey has not started. The provisions are packed. The destination is named. And the distance ahead is so vast that even the language we are using to discuss it, vast, huge, enormous, will collapse under its own weight before the night is over. We will need new ways of feeling these scales. We will need to anchor ourselves in our bodies as we go, because the numbers will try to pull us out of our bodies. The body is the only instrument we have for staying with what cannot be imagined. So here is the final thing to know before we leave. The edge of the universe is not a place we can ever physically reach. It is not a place anyone will ever physically reach. The deadline of light makes sure of that. What we are doing tonight is a journey of imagination, but it is an imagination grounded in measured fact. Every checkpoint we pass tonight is a real distance, a measured reality, a place that exists in the same sense your room exists. The space between you and the cosmic horizon is full, full of stars, full of galaxies, full of empty regions vaster than galaxies, full of structures we did not know existed even a generation ago. We are going to meet all of them, one layer at a time. Take one more breath here on the surface before we lift off. The air in your lungs is, in some sense, a piece of the planet you are about to leave. When you exhale, you are giving the Earth back a small share of itself. We will not breathe again until the journey is done. Now we turn to the layer just above the air, because once you understand how thin the atmosphere is, the next surprise is how thin the next layer is too. Low Earth orbit is the place where the International Space Station travels, where most satellites circle, where the astronauts you have seen photographed in floating poses make their home. It is roughly 400 kilometers above your head. 400. That is the distance between two ordinary towns. And yet, at that altitude, you are above the planet entirely, weightless, falling around the Earth in a long, curving arc, with the blue surface of the world rolling beneath you 16 times every 24 hours. If you want a sense of how local this is, hold up your hand at arm's length. The width of your palm, held that way, is roughly the angular size of the Earth as seen from the Moon. From low Earth orbit, the Earth fills your entire field of view. You are not yet looking at the Earth as a whole. You are still inside its visual embrace. The planet is so large from there that you can only see one continent at a time. The horizon curves softly. The air is a thin glowing crescent of blue, hugging the surface, separating the rock from the dark. From this height, you cannot see any human structure unaided. No cities, no roads, no walls. Even the brightest lights of human civilization, when they appear at night, are diffuse. They are smudges. They are not architecture. This is the closest layer to home, and it is already a layer where the human species barely lives. There are usually around 7 to 10 people in low Earth orbit at any given moment. The total number of human beings who have ever been there since the beginning of crewed spaceflight in 1961 is just over 700. That is a smaller population than a single small village. The entire human story of life beyond the atmosphere is told by a group of people who could fit comfortably in one auditorium. Beyond low Earth orbit, the next layer is the Moon, 384,000 kilometers away. That distance is 1,000 times farther than the space station, 1,000 times. If the space station is at arm's length, the Moon is across a small city. Light from the Earth takes about 1.25 seconds to reach the Moon. Light from the Moon takes 1.25 seconds to reach you. When you look at a full moon, you are seeing it as it was a heartbeat ago. The delay is small, but it is real. It is the first concrete reminder that nothing in the universe is seen now. Everything is seen as it was, even the Moon. 12 human beings have stood on the surface of the Moon. 12, the same number as the people sitting at a long dinner table. They went between 1969 and 1972 in the Apollo program, and then humans simply stopped going. We have not returned. The footprints of those 12 are still there, undisturbed, because there is no wind on the Moon, no rain, no erosion. The boot prints will last for millions of years before micrometeorites slowly grind them down. They are, in a sense, the most permanent monuments humans have ever made. 12 sets of footprints, the deepest extension of our species into space. We are about to go far past those footprints. We are about to walk past the Moon as if it were a doorstep. That is the picture so far. Earth at the center, atmosphere a thin shell, low Earth orbit a hand's breadth above. the moon 1,000 hands' breadths away, and beyond the moon, the empty space of the inner solar system where the planets ride. It could have been just rock and ice. It could have been just gas. It could have been a single planet alone in a quiet emptiness. But what we have is a system, a small family of worlds bound by a single sun. And to understand the journey outward, we have to understand how much room there is between those worlds. The sun is the gravitational center of our local neighborhood. It is a yellow-white star, an ordinary star by galactic standards, 8 light minutes away from us. 8 minutes. That is how long it takes light to travel from the sun's surface to your eyes. When you stand outside on a sunny morning, the sunlight on your skin is 8 minutes old. If the sun were extinguished now, you would not know for 8 minutes. The plants would not know. The Earth's orbit would not change for those 8 minutes. The light is a courier with a time delay built in. The sun is roughly 150 million kilometers from Earth. That distance is called 1 astronomical unit. It is the basic ruler of the solar system. Mercury is about 1/3 of 1. Venus is about 70%. Earth is 1. Mars is about 1.5. Jupiter is more than 5. Saturn is nearly 10. Uranus is around 19. Neptune is about 30. Pluto, when it is at its average distance, is about 39. The Kuiper Belt, the icy ring of small bodies beyond Neptune, extends to around 50. The heliopause, where the sun's wind of charged particles finally surrenders to the wind of the rest of the galaxy, is somewhere around 120. These numbers can blur, so anchor yourself with one image. If the sun were a basketball at the center of a city, the Earth would be a small marble about 30 meters away. Jupiter would be a tennis ball 150 meters away. Neptune would be a pea 900 meters away. The next nearest star would be another basketball, somewhere on the other side of the world. That is the shape of our solar neighborhood. A few small balls within walking distance of one bright sphere, and then nothing for a global distance, and then another sphere. We are going to walk through the inner solar system carefully, because the inner solar system is the only piece of the journey where humans have actually sent representatives. Past Neptune, we have nothing alive. We have only metal and silicon, ticking away on machines we sent decades ago, traveling slowly outward in directions no human being will ever follow. Mercury is the smallest of the 8 major planets and the closest to the sun. It is a world of bare rock, scarred by impact craters with no atmosphere worth mentioning. The day side reaches over 430 degrees Celsius. The night side falls to nearly -180. There is no air to carry heat from one side to the other. A spacecraft called Messenger, launched in 2004 by NASA, orbited Mercury from 2011 to 2015 and mapped its entire surface for the first time. We learned, among other things, that there is water ice in the permanently shadowed craters near Mercury's poles, hidden in pits where sunlight has not fallen for billions of years. Even on the planet closest to the sun, there is ice, because the geometry of light and shadow is unforgiving. Venus is the second planet, and in many ways the strangest. It is roughly Earth-sized, but its atmosphere is thick, sulfurous, and crushing. The surface pressure is about 92 times that of Earth's, equivalent to standing under nearly a kilometer of seawater. The clouds are made of sulfuric acid. The surface temperature is a steady 460 degrees Celsius, hotter than Mercury's day side, because the carbon dioxide in Venus's atmosphere traps heat with terrifying efficiency. Venus is what a runaway greenhouse looks like. It is a warning carved in physical law on a planet next door. The Soviet Venera probes in the 1970s and 1980s landed on the Venusian surface and survived only minutes before being destroyed. We have, to date, no continuous presence on Venus. The planet allows visitors only briefly. Mars is the fourth after Earth and the most familiar to us in popular imagination. Half the size of Earth, with a thin carbon dioxide atmosphere, frozen polar caps, and the rust-colored dust that gives it its red appearance. We have sent more than 50 missions to Mars. Most have failed. Some have succeeded extraordinarily. Viking 1 in 1976, the rover's Spirit, Opportunity, Curiosity, Perseverance, the Ingenuity helicopter that flew through the thin Martian air. We have looked at Mars more closely than any other planet beyond our own, and we still cannot say whether life ever existed there. The evidence of ancient water is overwhelming. Riverbeds, lake floors, mineral deposits that only form in the presence of liquid water. But whether anything ever lived in that ancient water remains, in 2024, an open question. Some researchers, like Caltech's Bethany Eilman, argue that the geology strongly suggests habitable conditions persisted long enough for microbial life to develop. Others remain cautious, noting that habitability is not the same as inhabitation. The question is open. The journey continues past it. Beyond Mars is the asteroid belt, a thin disk of rocky bodies between Mars and Jupiter. Despite the way it appears in films, the asteroid belt is mostly empty. If you were standing on one asteroid, you would almost never see another with the unaided eye. The total mass of all the asteroids combined is less than 4% of the Moon's. The belt is a sparse necklace, not a barrier. Then comes Jupiter, the largest planet by far, a gas giant more than 300 times the mass of the Earth. Jupiter is so massive that the Sun and Jupiter both orbit a common center of mass that lies just outside the Sun's surface. The other planets follow the Sun. Jupiter, in a sense, leads. Its great red spot is a storm wider than 2 Earths placed side by side, a storm that has been spinning for at least 400 years and possibly much longer. The Juno mission, which arrived at Jupiter in 2016 and is led by Scott Bolton at the Southwest Research Institute, has been mapping Jupiter's interior, its magnetic fields, its auroras, and its moons. The data have rewritten parts of what we thought we knew about gas giants. Jupiter does not have the simple layered interior we expected. Its core is fuzzy, smeared, dispersed across a much larger volume than predicted. Even our nearest giant is, in 2024, still surprising us. Saturn is the 6th, encircled by its famous rings, sheets of ice and rock fragments orbiting in a disk so flat and wide that it would stretch from Earth to roughly 2/3 of the way to the Moon. The Cassini mission, which orbited Saturn from 2004 to 2017, gave us detailed views of the rings, the storms, the moons. 2 of those moons, Titan and Enceladus, may be among the most likely places in the solar system for life beyond Earth. Titan has lakes of liquid methane and a thick nitrogen atmosphere. Enceladus has a subsurface ocean of liquid water beneath an icy crust, and that ocean vents into space through cracks at the South Pole, throwing plumes that Cassini flew through and sampled. The plumes contained organic molecules. We do not know if there is life in that ocean. We do not yet have the means to find out. The journey continues past it, but the question is left planted, like a seed in the ground. Beyond Saturn are Uranus and Neptune, the 2 ice giants. They are smaller than Jupiter and Saturn, but still much larger than Earth. They are colder, dimmer, and visited only once each in the entire history of human exploration. By Voyager 2, which flew past Uranus in 1986 and Neptune in 1989. Voyager 2 took the only close-up images we have of those two worlds. After it passed Neptune, it kept going. It is still going. Both Voyager 1 and Voyager 2, launched in 1977, are now in interstellar space. They are the farthest human-made objects in existence. They are the deepest representatives of the human species into the void. They will outlive the Earth. Picture them for a moment, those two probes. Each is the size of a small car, gold-plated, equipped with a phonograph record etched with sounds and images from Earth, drifting outward at around 61,000 kilometers per hour, a speed that on the scale of cosmic distances is a slow walk. Voyager 1 is currently nearly 26 billion kilometers from Earth, on track to reach one full light day from us in late 2026. The light from Earth takes more than 23 hours to reach it. When the Deep Space Network sends a command, the signal arrives almost a full day later, and the response takes another full day to come back. The probe is still functional. Its plutonium power supply is fading, but it is still talking to us, faintly, from a distance no human eye could meaningfully picture. And on the scale of tonight's journey, Voyager 1 is barely past the doorstep. It has traveled in nearly 50 years, about 1/5,000th of a single light year. The nearest star is more than 4 light years away. Hold that. Hold the slow walk. The Voyagers are the fastest, farthest representatives of our species, and they have not finished even a 5,000th of the gap to the next star, after almost half a century of unbroken outward travel. This is the deadline of light beginning to bite. Even our best couriers are too slow. We are now at the edge of the heliosphere, the bubble of solar wind that the sun blows out around itself. The boundary is called the heliopause, and Voyager 1 crossed it in 2012, at a distance of about 120 astronomical units from the sun. That was the moment the probe officially entered interstellar space. It was no longer in the wind of the sun. It was in the wind of the galaxy. The composition of charged particles around it changed. The magnetic field shifted. For the first time in the history of any human-made object, a piece of our civilization was outside the sun's influence. Take a breath here. Stay with this image for a moment. Voyager 1, alone, drifting in the cold, thin wind of the galaxy, broadcasting its faint signal back toward a small blue planet that it can no longer see, where the engineers who built it are mostly retired or dead, and where the species that launched it is still arguing about what to do next. The probe does not know any of this. It just keeps measuring. It keeps reporting. The gold record on its side carries greetings in 55 languages, recorded in 1977, on the assumption that someday, somewhere, in a future too distant to reasonably anticipate, something might find it. This is where humans end. Beyond the heliopause, we have sent nothing alive. We have sent 2 metallic representatives, neither of which knows it is a representative, and a small handful of other probes that have not yet crossed the boundary. Pioneer 10, Pioneer 11, New Horizons, which flew past Pluto in 2015 and is still moving outward. 5 small machines in total are leaving the solar system. 5. Beyond the heliopause is the Oort cloud, a vast spherical shell of icy bodies that extends from roughly 2,000 to as far as 100,000 astronomical units from the sun. The Oort cloud is so large that it makes up the bulk of the gravitational territory of the solar system. The planets, the asteroid belt, the Kuiper belt, All of them are inside a thin disk near the center. The Oort cloud is a nearly spherical halo around it all, made of comets and small icy worlds, most of them smaller than mountains. When a long-period comet swings into the inner solar system, it has fallen from the Oort cloud. Halley's Comet is from there. The Hale-Bopp Comet of 1997 was from there. They are messengers from the outermost sphere of the Sun's territory. The Oort cloud is so thinly populated that if you were standing on one of its bodies, you would almost certainly never see another. The sky would be full of stars, but the closest sibling object might be tens of millions of kilometers away. The Sun, from the outer Oort cloud, would be a moderately bright star, visible, recognizable, but not warming. There would be no day there, just a permanent night with one slightly brighter point in it, a point that, on closer inspection, has a small blue speck orbiting it that contains your entire history. The Voyager probes will not reach the inner Oort cloud for another 300 years. They will not reach the outer edge for tens of thousands of years. They will be drifting through the Oort cloud while empires rise and fall on the planet they came from, while glaciers come and go, while species evolve and disappear. They will simply keep moving. By the time they reach the cloud's outer edge, they will be inert. The plutonium will be exhausted. They will be cold artifacts moving outward by inertia alone. And yet they will still be inside the gravitational reach of our Sun, still inside the solar system, in the broadest definition of that term. That is what the Sun's territory looks like. A core of planets within a few light hours, a halo of icy worlds extending to nearly 2 light years. And only beyond that does the territory of the next star begin. Now we approach the first true threshold of the journey, the interstellar void, the cold passage between stars. Once we cross this, we will not be inside any star's territory. We will be in the long darkness between, where nothing keeps you company except the slow drift of the galactic wind and the distant glitter of 100 billion suns. The nearest star to ours is Proxima Centauri, a small red dwarf about 4.24 light-years away. It is part of a triple star system, the Alpha Centauri system, which also contains 2 larger Sun-like stars called Alpha Centauri A and B. These 3 stars are bound to each other gravitationally. Proxima Centauri orbits A and B at a great distance, taking perhaps 500,000 years to complete one orbit. They are, together, our nearest stellar neighbors. 4 light-years is, on the scale of tonight's journey, almost nothing. It is the next room. It is the doorstep beyond the doorstep. And yet, with our current technology, we cannot reach it. The Voyagers will not even pass close to the Alpha Centauri system, because they are not heading in that direction. Even if they were, they would take more than 70,000 years, and there is no way with any propulsion system we currently know how to build to reach Alpha Centauri in a single human lifetime. A handful of theoretical proposals. Breakthrough Starshot, for instance, which proposes accelerating a fleet of tiny probes with massive ground-based lasers to about 20% of the speed of light, might one day deliver a small probe in a few decades. But for a human being, in a human ship, the journey to even the next star is, with our current understanding of physics, beyond reach. This is the first stretch where the size of the room defeats us. Inside the solar system, we can send things, even if slowly. To the next star, we cannot send anything that will arrive while the senders are still alive. This is the edge of what the human species, as it currently exists, can practically reach. We have not been beyond it. We will not be beyond it for some time. Perhaps for a very long time. So we leave the solar system in our minds, but only in our minds. We pass the heliopause. We pass the Oort cloud. We enter the interstellar medium, the thin gas and dust between stars, where the density of matter is roughly 1 atom per cubic centimeter. That is, you would have to fill a volume the size of a small refrigerator to gather a single milligram of matter. The interstellar medium is a vacuum so deep that it would be considered an excellent laboratory vacuum on Earth. It is dark. It is cold, around 3 degrees above absolute zero, which is the temperature of the cosmic background. It is silent. There is no air to carry sound. There is no air at all. And yet, even here, things happen. Charged particles stream from the sun and from other stars. Magnetic fields thread the medium. Cosmic rays, high-energy particles from violent events in the galaxy, pass through everything, including you, all the time. Right now, inside your body, several muons from cosmic ray showers are passing through, harmlessly, at nearly the speed of light. The interstellar medium is empty in the sense that there is almost no matter, but it is full in the sense that radiation and fields run through it constantly. It is a medium. It is the connective tissue of the galaxy. We are now in that connective tissue, on our way to Alpha Centauri. We will arrive there at the next checkpoint, 4.24 light-years, the distance to the nearest star. If you could ride a beam of light, you would arrive in 4 years and 3 months. If you rode the Voyager's speed, you would arrive in 75,000 years. The mismatch between those two numbers is the first concrete demonstration of how badly outmatched any conceivable spacecraft is by the size of the gap between stars. Imagine arriving. Alpha Centauri A is a sun-like star, slightly larger and slightly brighter than our own. Alpha Centauri B is smaller, an orange dwarf, and the two of them orbit each other at a distance that varies between roughly the orbit of Saturn and the orbit of Pluto. You would see 2 suns, close enough together to look like a binary system from a planet that orbited either of them, far enough apart that they would not merge into a single point. And in the distance, perhaps 1/10 of a light-year out, the small red eye of Proxima Centauri, faint but unmistakable. Around Proxima, at least 3 planets have been confirmed. The closest of them, Proxima B, was discovered in 2016 by a team led by Guillem Anglada Escudé. It sits in what astronomers call the habitable zone, the range of distances at which liquid water could in principle exist on a planetary surface. Whether life could survive there is uncertain. Proxima Centauri is a flare star. It throws violent bursts of radiation at unpredictable intervals, the kind of bursts that could strip a planet's atmosphere if no magnetic field protected it. We do not know if anything lives there. We may never know. The closest star system to our own is, in 2024, still a place we can study only with telescopes. We have never sent a probe. We may never send one. But the system is real. The planets are real. The light reaching us from Alpha Centauri tonight left those stars in 2020. You are looking, when you look at that part of the sky, at a moment that has already passed. Now expand outward. The neighborhood around the sun, within roughly 15 light-years, contains about 50 stars. That sounds like a lot, but they are spread thinly. The average distance between neighboring stars in our part of the galaxy is several light-years. Stars are vanishingly small targets in vast oceans of empty space. If you were a beam of light traveling through the galaxy, you could fly for centuries without coming close to any star. The galaxy looks dense in photographs because each pixel of the photograph represents a region of space many light-years across. At the actual scale, if the sun were a basketball in one city, The next nearest star would be another basketball in another city, far away. The galaxy is mostly emptiness with bright objects scattered through it. There is a name for the small bubble of relatively low-density gas around our sun. It is called the local bubble. It extends for about 300 light-years in various directions, and inside it, the interstellar medium is unusually thin. The local bubble was probably carved out by supernova explosions over the last 10 or 15 million years. Perhaps 15 or so massive stars detonating in sequence, each one blowing the surrounding gas outward, leaving a long-lived cavity behind. We are inside that cavity. Our solar system is currently passing through it, on a trajectory that will eventually carry us out the other side in some tens of millions of years. The sun is not stationary. Nothing in the galaxy is stationary. Every star is in motion, sweeping along its own path through the spiral arms. The sun's path takes it around the center of the Milky Way once every 225 million years, more or less. That period is sometimes called a galactic year. The sun has completed roughly 20 galactic years since it formed. The dinosaurs lived roughly 1 galactic year ago. The first multicellular life, more than 3. The sun has carried Earth through the spiral arms many times, into denser regions, and then out again, into clouds of gas, and then out again, past hundreds of supernovae and stellar nurseries and dark molecular clouds, all without losing the planets. The orbit of the Earth around the sun has been steady for 4.5 billion years. The orbit of the sun around the galaxy has been steady for as long as the sun has existed. We are riding inside a much larger motion than we usually notice. Now, picture the galaxy itself. The Milky Way is a barred spiral galaxy, roughly 100,000 light-years across. It contains, by current estimates, somewhere between 100 billion and 400 billion stars. The number is uncertain because most of the stars are small, dim red dwarfs that are hard to count from a distance. The sun lies in one of the spiral arms, the Orion Arm, about 26,000 light-years from the galactic center. 26,000 light-years. The light from the center of our own galaxy left when the last ice age was at its coldest, when humans were first painting on the walls of caves in southern Europe, when the great mammoths still walked across the steppes. The center of our galaxy, as we see it tonight, is showing us its appearance during the human Paleolithic. The galactic core, that bright bulge of densely packed stars at the heart of the Milky Way, is older to our eyes than human civilization itself. At the very center of the galaxy lies a supermassive black hole called Sagittarius A star. It has a mass of about 4 million suns, packed into a volume smaller than the orbit of Mercury. The Event Horizon Telescope collaboration in 2022 released the first direct image of Sagittarius A star, a dark central shadow surrounded by a glowing ring of superheated gas. That image was the result of an international effort spanning years and continents, combining data from telescopes on 6 different mountains across the world to create a virtual telescope the size of the Earth. Heino Falke, one of the project's long-standing theorists, had argued for decades that such an image was possible. He turned out to be right. The image showed us a thing we had only inferred, a massive black hole tucked at the center of our own galaxy, around which all of the Milky Way's stars are gravitationally arranged. Sagittarius A star is not the largest black hole we know of. It is small as supermassive black holes go. But it is ours. It is the gravitational anchor of the place we live. Pull back further. The galaxy is a vast, slowly rotating disk. The arms are not rigid structures, but density waves, regions where stars and gas pile up briefly as they pass through, then move on. Star formation is concentrated in the arms because that is where the gas is densest. The young, hot, blue stars trace the arms most clearly. Older stars are spread more evenly through the disk. The galactic halo, a roughly spherical region around the disk, contains globular clusters, ancient, tightly bound balls of stars that orbit the center on highly inclined paths. Many of those clusters are nearly as old as the universe itself, more than 12 billion years old. They are the elders of the galaxy. If you could see the Milky Way from outside, you would see something extraordinarily beautiful. A disk of light, 4 spiral arms swirling around a bright central bulge, threaded with dark lanes of dust, surrounded by a faint glow of older stars. From above, it would look like a slowly turning pinwheel of fire. From the side, like a thin, luminous wafer with a bulge in the middle. The color would shift. Older regions would glow yellow and red. Star-forming arms would shine blue. The dust lanes would be black streaks across the brightness. We will never see it from outside. No human will ever step outside the Milky Way. The galaxy is too large and we are too slow. The fastest probes we could conceivably build, even hypothetically, would take millions of years to reach the edge of the galactic disk. We are inside the pinwheel. We will stay inside. The view from inside is the view we have, which is the long band of light we call the Milky Way, stretched across the night sky. That band is the disk seen edge-on from a position embedded in it. Every glimmering point in that band is a star within our own galaxy. Every dark patch is a cloud of dust. We see the galaxy from the inside out. The total number of stars in the Milky Way, even at the lower estimate, is so large that if you tried to count 1 star per second without ever stopping to eat or sleep, it would take you more than 3,000 years to finish. And the Milky Way is just one galaxy. That is the next thing the journey requires you to absorb. The Milky Way is not the universe. The Milky Way is one galaxy among approximately 2 trillion. 2 trillion galaxies, each one with hundreds of billions, sometimes trillions of stars. Each one with planets. Each one, in some statistical sense, with the conditions necessary for the kinds of physics and chemistry that produced you. 2 trillion. The word does not register in the human nervous system. It is a number we know how to write down, but cannot picture. So do not picture it. Just feel it. Feel the size of the room expanding once more. The galaxy is vast. The galaxy is, on the scale of the journey, a single grain. 2 trillion grains, each with hundreds of billions of stars, each with planets, each separated from its neighbors by stretches of space larger than themselves. The next layer outward is the local group, a small cluster of galaxies bound together by gravity. The local group contains about 80 members, but most of them are small dwarf galaxies. The 2 dominant members are the Milky Way and the Andromeda Galaxy, with the Triangulum Galaxy as the 3rd largest. The other members orbit one or both of these. Andromeda is 2.5 million light-years from us. That is the next major checkpoint. The light from Andromeda that reaches your eyes tonight left when our ancestors were just beginning to walk upright on the African savanna, when the first stone tools were being shaped, when the genus Homo was emerging from earlier hominids. Andromeda's light is older than every human story ever told. By the time you see it, 2.5 million years of the planet's history have passed. The image of Andromeda you can see with your unaided eye on a dark night is a fossil. A bright fossil, larger than the full moon in angular size, but a fossil nonetheless. Andromeda is also currently on a collision course with the Milky Way. The two galaxies are falling toward each other at about 110 kilometers per second. They may meet in a slow gravitational embrace in roughly 4 to 5 billion years, though recent analyses with Gaia data suggest the collision is no longer guaranteed, with current models estimating roughly even odds within the next 10 billion years. When they do, the result will not be a violent crash. Galaxies are mostly empty space, and individual stars almost never collide. Instead, the two disks will pass through each other, twist into long tidal streamers, fall back, and over hundreds of millions of years merge into a single elliptical galaxy. Astronomers sometimes call the future merged galaxy Milkomeda, half-jokingly. The Sun, by then, will be near the end of its life as a stable star, beginning to swell into a red giant. Whatever planets remain in our system will see the night sky transformed. Andromeda, instead of being a faint smudge, will fill the sky. Then the two galaxies will tangle, and the night sky will become something no human will ever see, because no human will exist when it happens. Hold the strangeness of that. There is a future already written in the gravitational equations, where the night sky of Earth is filled with the disk of another galaxy. That sky exists, in the same sense that next Tuesday exists. It is simply very far ahead. The geometry that produces it is already in motion, already locked in. We are in the early stages of an inevitable collision, and we cannot do anything to alter it, and we will not live to see it. Our descendants, if any survive, may, or they may not. The 2.5 million light years between us and Andromeda will close. The room will draw together. The local group is small as cosmic structures go, about 10 million light years across. Inside it, the gravity of the member galaxies overwhelms the general expansion of the universe. The local group is not flying apart. Its members are bound. They will continue to orbit and merge and drift among each other for as long as gravity holds them. Beyond the local group, the structure changes again. The local group is part of a larger structure called the Virgo supercluster, which is in turn part of a still larger structure called the Laniakea supercluster. Laniakea, a name from Hawaiian meaning immeasurable heaven, was identified in 2014 by an astronomer named Brent Tully and his colleagues. They mapped the motions of thousands of nearby galaxies and noticed that, despite the general expansion of space, certain galaxies were flowing in coordinated patterns toward common gravitational centers. By tracing the flow lines, they identified a region of about 500 million light-years across, in which all the galaxies were drifting toward a particular gravitational anchor called the Great Attractor. Laniakea is our home supercluster. The local group sits near one edge of it. The Great Attractor is somewhere near the center. We are flowing toward it slowly, along with thousands of other galaxies, like leaves drifting on a vast invisible current. The Great Attractor is hidden behind the dust of our own galaxy, partially obscured from direct observation, but we can feel its gravitational pull through the motions of the things around it. It is, in a sense, the unseen center of our local cosmic neighborhood. But Laniakea is not the universe. Laniakea is itself a node in a still larger structure. Beyond Laniakea, the universe organizes itself into what cosmologists call the cosmic web. Filaments and walls and sheets of galaxies, separated by enormous voids where almost no galaxies exist at all. Pictures of the cosmic web look like neural networks, or like the foam in a glass of beer, or like the slow tangling of a vine over a wall. Galaxies sit along filaments. Clusters of galaxies sit at the intersections of filaments, and between the filaments are voids, empty regions, sometimes hundreds of millions of light years across, where you could travel for an eternity and see almost nothing. The largest known voids in the universe are remarkable. The Voyager void, discovered in 1981 by Robert Kirshner and his colleagues, is roughly 330 million light-years across. Inside it are perhaps a few dozen galaxies, where, in a similarly sized region of more typical density, you would expect thousands. If our Milky Way were inside the Voyager void instead of where it is, our ancestors would have looked up at a sky containing only a handful of galaxies, separated by enormous gulfs. The night would be much emptier. The universe would feel much lonelier. We are lucky, in a sense, to live in a relatively dense filament. Our sky is full because we are not in a void. Other voids are even larger. The Eridanus supervoid, identified in the early 2000s, may be 1 billion light-years across. We do not yet fully understand it. Some researchers think such large voids may be regions where the cosmic microwave background, the leftover radiation from the early universe, appears slightly cooler than average, possibly because light passing through such a void experiences a slight change in energy due to the void's geometry. Others argue that other explanations, statistical fluctuations or large-scale structure effects, can account for the cool spot. The debate is open. Now stand back in your imagination, far enough that you can see the cosmic web as a whole. Imagine that you can see hundreds of millions of light-years in every direction. The galaxies are no longer individual points. They are dust on the strands of a web. The strands form long, slow curves that connect cluster to cluster across enormous distances. The spaces between the strands are dark, not absolutely empty, but very, very thinly populated. The web is what the universe looks like at the largest scales we can imagine. It is the largest known structure of any kind. Beyond it, on still larger scales, the universe begins to look smooth and uniform, the same everywhere, in every direction. That uniformity is one of the deepest facts about our cosmos. It tells us, among other things, that whatever produced the universe produced it in a way that left almost no preferred direction, no preferred place, no center. There is no center. That is one of the most important facts we have learned about the universe in the last 100 years. There is no central point from which everything is expanding. Every observer in every galaxy sees themselves at what appears to be the middle. From our position, the universe seems to extend equally in every direction, with the most distant things receding from us at the highest apparent speeds. From any other position in the universe, an alien astronomer would see the same thing, themselves at the apparent center, surrounded by a sphere of receding galaxies. Both observers would be correct in the sense that there is no privileged center. The expansion is not an explosion that started at a point. It is a stretching of the entire fabric. Every part of space is moving away from every other part. Every position is, in that sense, the middle. This is one of the hardest things in cosmology to feel in the body, because the body has only ever known explosions, things that begin at a point and spread outward. That is not what happened. The Big Bang was not an explosion in space. It was an event in space itself. The thing that began was the geometry, and the geometry has been stretching ever since. Take a breath here. You are now thinking about the largest single fact about the universe, that it has no center, and that every part of it is, in a sense, the middle. The number of philosophical implications of this fact is enormous. We will return to them. For now, We have reached the scale where the cosmic web is the dominant structure, where the local group is a small node, where our galaxy is a single grain of dust on one strand, and where our solar system is, on this scale, invisible. We have effectively disappeared from the picture. We are too small to see. The room is now hundreds of millions of light years away. We are not a feature. There is one more thing to address before we keep going outward. We need to talk about how we know any of this. Because the temptation, when you hear numbers like 2 trillion galaxies and 46 billion light years, is to assume that someone made these up, or that they are too speculative to take seriously. They are not. They are some of the most rigorously measured numbers in the history of human knowledge. The basic technique is called the cosmic distance ladder. You measure the distance to nearby objects using one technique, then use those distances to calibrate a second technique that works at greater distances, and you keep stepping outward. The first rung is parallax, measuring the apparent shift of nearby stars against the background as the Earth moves around the Sun. The shift is tiny but measurable. It gives us distances to stars within a few hundred light years. The Hipparcos satellite in the 1990s and the Gaia satellite, beginning in 2013, mapped the precise positions and distances of more than 1 billion stars in the Milky Way using this technique alone. Gaia, led for years by Anthony Brown of Leiden University and his colleagues, has produced the most detailed three-dimensional map of our galaxy ever made. Beyond parallax, we use standard candles, objects whose intrinsic brightness we know, so that by measuring how bright they appear, we can calculate their distance. Cepheid variable stars, certain types of pulsating stars whose period of pulsation is tied to their intrinsic brightness, were first calibrated by Henrietta Swan Leavitt at Harvard in 1912. Her work allowed Edwin Hubble, in 1924, to demonstrate that what were then called spiral nebulae were actually distant galaxies far outside the Milky Way. Until Hubble's measurement, many astronomers had believed the Milky Way was the entire universe. After Hubble's measurement, we knew that the universe extended unimaginably far beyond it. Beyond Cepheids, we use Type 1a supernovae, exploding white dwarfs whose peak brightness is also calibrated. They are bright enough to be seen across most of the observable universe. By measuring their light curves and their redshifts, we have measured the expansion history of the universe with extraordinary precision. In 1998 and 1999, two competing teams, one led by Saul Perlmutter at Berkeley, the other led jointly by Brian Schmidt and Adam Rees, independently announced that the expansion of the universe was accelerating. Both teams shared the 2011 Nobel Prize in Physics for that result. The acceleration attributed to a poorly understood property of empty space, called dark energy, is the deadline written into the universe. We will return to it shortly. The point is that our knowledge of cosmic distances is not a guess. It is a layered, cross-checked, painstakingly built structure of measurements that has been refined by thousands of researchers across more than a century. The distances are real. The galaxies are real. The horizon is real. So with that confidence anchored, we can keep going. We have descended through every familiar layer: the room, the atmosphere, the orbit of the moon, the solar system, the interstellar void, the galaxy, the local group, Laniakea, the cosmic web. We are now traveling at scales where the structure of the universe itself becomes our subject. Beyond a few 100 million light years, the question is no longer what is in this region, but what does the universe look like as a whole? pull back once more. Imagine that the entire cosmic web, all the filaments, all the voids, all the clusters and superclusters we have just discussed, fits inside a single image. Now imagine that image as one small region of the observable universe, and that the rest of the observable universe extends far beyond it in every direction, full of similar webs. From the very largest scale, the universe looks smooth. The clumpiness disappears at distances of a few billion light years. Beyond that scale, every region looks essentially the same. Same density, same composition, same kinds of structures, same statistical patterns of galaxies and voids. This uniformity has a name. Cosmologists call it the cosmological principle. It is the assumption, and now the well-supported observation, that the universe on the largest scales is the same everywhere, not literally identical. The exact arrangement of galaxies in one region differs from another, but the average properties are the same. There is no special place. There is no edge in the sense of a boundary you could find by traveling far enough. The universe, to the best of our measurement, is uniform. The cosmological principle is one of the deepest assertions ever made about the world. It says that the laws of physics that work on Earth work everywhere. It says that hydrogen behaves the same way 10 billion light years from here as it does in the sun's core. It says that gravity pulls in the same way in the Boötes void as it does in the Coma cluster. It says that we are not special, our location is not special, our era is not specially favored. We are one of an enormous number of equally valid vantage points on the same vast uniform fabric. For most of human history, we believed the opposite. We believed that we were at the center, that the heavens turned around us, that the earth was the focal point of creation. The slow erosion of that belief, first by Copernicus, then by Galileo, then by Hubble, then by the cosmic microwave background measurements of the 1960s and 1990s and 2000s, has been one of the longest and most painful intellectual journeys our species has taken. We had to give up being the center. We had to give up being unique. We had to accept being one observer among an essentially uncountable number of equivalent positions. The acceptance is not complete. There are still many people who feel in their bodies that the world is centered on them. The cosmological principle says it is not. The universe is the same everywhere. You are not in a privileged seat. You are simply in a seat. Like everyone else, everywhere else. That truth is at once liberating and lonely. It tells you that you are not the protagonist of the cosmos. It also tells you that everywhere is, in some sense, home. There is no place where the rules are different. The hydrogen in your body and the hydrogen in the most distant quasar follow the same laws. We are made of the same stuff, organized in the same way, behaving according to the same principles. The universe is, in that sense, a single object, a single fabric, stretched, folded, clumped in places, but one continuous thing. Now we approach a new layer, the cosmic microwave background, the oldest light in the universe. When astronomers point their telescopes outward, they see galaxies at greater and greater distances. Each galaxy, because of the speed of light, is seen at an earlier and earlier time. A galaxy 1 billion light years away is seen as it was 1 billion years ago. A galaxy 10 billion light years away is seen as it was 10 billion years ago. As we look outward, we look backward. The universe gives us its history, written along the line of sight. Eventually, if we look far enough, we should see the very first galaxies. And beyond them, we should see a time before galaxies existed. A time when the universe was simply an enormous cloud of hot gas, glowing with its own heat. That time was about 380,000 years after the Big Bang, when the universe had cooled enough for protons and electrons to combine into neutral atoms. Before that moment, the universe was opaque. Free electrons scattered light constantly. Photons could not travel in straight lines. After that moment, the universe became transparent. Photons could travel freely for the first time. The light released at that moment has been traveling ever since. That light is the cosmic microwave background. It is, in a literal sense, the wall of our observable universe. It is the oldest electromagnetic signal that exists. It comes from every direction. It fills the sky uniformly, bathing the Earth in a faint, almost perfectly even glow at microwave wavelengths. When you stand outside on a clear night, you are surrounded by the cosmic microwave background. You cannot see it with your eyes. Your eyes do not detect microwaves. But it is there, passing through you, passing through the air, passing through everything. About 1% of the static you used to see on old analog television sets, when there was no broadcast signal, was caused by photons of the cosmic microwave background hitting the antenna. You have, in a sense, watched the early universe on television. The early universe was speaking to you in static. The cosmic microwave background was discovered in 1964 by Arno Penzias and Robert Wilson, two radio astronomers at Bell Labs in New Jersey, with their findings formally published the following year. They had been trying to use a radio antenna for telecommunications research, and they kept finding a faint, unexplained noise that came from every direction in the sky. They cleaned the antenna. They removed pigeon droppings. They ruled out every local source. The noise persisted. They eventually realized, with the help of theorists at Princeton who had been predicting just such a signal, that they had stumbled on the leftover heat of the Big Bang. They received the Nobel Prize in 1978. The cosmic microwave background became the strongest single piece of evidence for the hot Big Bang model of cosmology. Since then, 3 space missions have mapped the cosmic microwave background in increasing detail. COBE, in the early 1990s, led by John Mather and George Smoot, confirmed that the radiation has the spectrum of a perfect blackbody at a temperature of 2.725 Kelvin, meaning it has the exact spectral shape that hot, dense matter in thermal equilibrium would emit, which is precisely what the early universe was. Mather and Smoot shared the 2006 Nobel Prize for that result. WMAP in the 2000s mapped the tiny temperature variations in the background, fluctuations of 1 part in 100,000, the seeds from which all later structures would grow. Planck, launched by the European Space Agency in 2009, mapped those variations with even greater precision, and from its data, we have derived the most precise values we have for the age of the universe, its composition, and its expansion history. The age of the universe, from Planck data, is 13.8 billion years, plus or minus a few tens of millions. That is the number with which this script began. It is not a guess. It is the result of fitting an enormous multi-parameter cosmological model to the entire pattern of fluctuations in the cosmic microwave background. The same data tell us, to within a few percent, what the universe is made of. About 5% ordinary matter, the stuff of stars and planets and bodies. About 27% dark matter, a kind of matter that interacts gravitationally but not electromagnetically, that we cannot see directly, but whose presence we infer from its effects on visible structure. About 68% dark energy, the the strange property of empty space that is causing the expansion of the universe to accelerate. 5% ordinary, 27% dark matter, 68% dark energy. Stay with that breakdown. Most of the universe is something we do not understand. The matter you are made of, the matter the stars are made of, the matter the entire luminous universe is made of, is a small fraction of the total. The rest is invisible to us. We can detect it. We can measure its effects. We cannot, with current instruments, see it directly. Some researchers, like Vera Rubin and Kent Ford, who in the 1970s measured the rotation curves of galaxies and found that galaxies rotate as if they contain far more mass than their visible matter suggests, were among the first to demonstrate that dark matter must exist. Others have spent decades trying to identify what dark matter is. WIMPs, weakly interacting massive particles, axions, sterile neutrinos, primordial black holes. None of these candidates has yet been directly detected, despite years of careful experiments in deep underground laboratories like the Sanford Lab in South Dakota and the Gran Sasso Lab in Italy. Some researchers, like Mordechai Milgram in the 1980s, have proposed that dark matter is not a substance at all, but a sign that gravity itself behaves differently at large scales, a theory called modified Newtonian dynamics. Other researchers argue that this theory cannot account for all the observations. The debate is, in 2024, still active. The truth is uncertain. Dark energy is even stranger. It is the property of empty space that pushes the universe apart. Einstein, in 1917, introduced a term in his equations called the cosmological constant, a tiny additional force that he thought was needed to keep the universe static. He later removed it, calling it his greatest blunder, when Hubble showed the universe was expanding. But the cosmological constant came back in 1998 when the supernova teams found that the expansion was accelerating. The simplest explanation is that empty space has its own energy, and that energy pushes outward. The cosmological constant has reappeared. Some researchers, like Lisa Randall at Harvard, suspect that dark energy may be related to the geometry of higher dimensions or to as yet undiscovered properties of the vacuum. Others, like Adam Rees and his collaborators, focus on more precisely measuring how the expansion has changed over cosmic time, looking for clues. We do not know what dark energy is. We know what it does. What it does is set the deadline. The universe is expanding. The expansion is accelerating. The acceleration means that the most distant galaxies are receding from us faster and faster. Eventually, and this is the truly disturbing part, they will be receding faster than the speed of light. They will not violate special relativity because the recession is due to the stretching of space, not to motion through space. But the practical consequence is the same. Light from those galaxies will not be able to reach us. The space between us is growing too fast. Their light, sent toward us, will be carried away by the inflation of the gap. This means that the observable universe, the part of the cosmos we can in principle see, is getting smaller in a sense that matters. New galaxies are not appearing on the horizon. Old ones are disappearing beyond it, one by one, as the expansion outpaces their light. Eventually, in tens of billions of years, almost every galaxy currently visible to us will have crossed the cosmic horizon. The night sky of a future Earth, if Earth still existed, would be empty. Only the few galaxies bound to ours by gravity, the merging Milky system, and a handful of dwarfs would remain visible. Everything else would have receded into invisibility. We are living in a privileged epoch for cosmology. We can see the cosmic microwave background. We can see 2 trillion galaxies. We can deduce the history of the universe by looking outward in space and backward in time. Future astronomers on planets that may not yet exist will not have these advantages. They will see only their local cluster. They will not have the data to deduce the Big Bang. They will not have the cosmic microwave background to read. The history of the universe will, for them, be hidden behind a darkening sky. We are seeing the universe at the brightest moment in the entire arc of cosmic history, the moment most rich with information, the moment most legible. We will have to come back to that. For now, the deadline is enough. The horizon is closing. The room is, in the long run, going to empty. But before it empties, we still have a horizon to reach. We are still in this journey traveling outward, so we keep going. Now we turn to the strange half-visible region beyond the local universe, the realm of distant galaxies, the realm of redshifts greater than 1, the realm where the light has been traveling for billions of years before reaching us. A redshift of 1 means the light's wavelength has been doubled by the expansion of space. A redshift of 2 means it has been tripled. A redshift of 7, which corresponds to galaxies seen as they were less than 1 billion years after the Big Bang, means the wavelength has been stretched by a factor of 8. The visible light those galaxies emitted now arrives as deep infrared. The James Webb Space Telescope, launched in 2021, was designed to see exactly this kind of light. It is an infrared observatory, parked at a gravitationally stable point about 1.5 million kilometers from Earth, where it can see the early universe in the wavelengths the universe has stretched its light into. The James Webb has since 2022 been delivering images of galaxies at greater distances and earlier times than any previous instrument. Some of these galaxies, observed at redshifts of 10, 11, even 14, are seen as they were just a few 100 million years after the Big Bang. The light from them has been traveling for over 13 billion years. The space between has stretched so much during that travel that those galaxies are now, in the present, more than 30 billion light-years from us. We see them as they were when the universe was an infant. They themselves, if they still exist, have evolved and aged just as our galaxy has. Many of them will have merged with neighbors, transformed beyond recognition, possibly even ceased to exist in their original form. The image we see is not of them now. It is of them then. A few of the highest redshift galaxies the James Webb has detected are unexpectedly bright and unexpectedly mature for their age. They contain too many stars. They are too well organized. They look as if they had hundreds of millions of years of star formation already behind them, when the universe was only 300 or 400 million years old. This is, in 2024, a real puzzle. Some researchers, like Joel Leger at Penn State, argue that we may need to revise our models of how galaxies form in the very early universe. Others suggest that some of the brightness is being misinterpreted, that the redshift estimates may be slightly off, or that early galaxies were unusually compact and therefore appear brighter. The puzzle is open. James Webb is still gathering data. The picture of the early universe is shifting under our feet as we speak. Beyond the most distant galaxies lies a phase astronomers call the cosmic dawn, the time when the very first stars formed, perhaps as early as 150 million years after the Big Bang. We have not yet directly observed individual first-generation stars. They were probably very massive, very short-lived, and almost entirely made of hydrogen and helium, with virtually no heavier elements, because heavier elements had not yet been forged. They lived briefly, exploded as supernovae, and seeded the universe with the first carbon, oxygen, nitrogen, iron. Every atom heavier than helium in your body, every atom of carbon, calcium, potassium, iron, was forged inside a star and released into space when that star died. The atoms of your body are, almost without exception, recycled stellar matter. Some of them may have been forged in the very first generation of stars, more than 13 billion years ago. You are, in the most literal sense, made of dead stars. So is everything you have ever loved. Hold that for a moment. Stay with it. The atoms in your fingertips, the iron in your blood, the calcium in your bones, the carbon in your DNA were not made on Earth. They were made from stars that have been dead for billions of years. The sun did not make them. The sun is too small to forge most heavy elements. They were made in older, larger stars that lived and died before the sun was even a cloud of gas. Their light reached Earth, in a sense, twice. Once as light and again as the matter that became us. Before the cosmic dawn, before the first stars, the universe was a hot, dense, opaque plasma. The gas was too uniformly distributed to collapse into stars yet. The temperature was still too high. Protons and electrons were dancing around each other, but not yet combined. It is in this era that the cosmic microwave background was created. At the moment, the universe finally cooled enough for atoms to form and light to escape. Before that, no light could travel freely. Before that, the universe was, in a sense, blind to itself. We cannot see directly into the era before the cosmic microwave background. The opaque plasma blocks our view. Whatever happened in the first 380,000 years is hidden behind that wall. But we can deduce a great deal. We know that the universe was much hotter, much denser, and that it expanded and cooled rapidly. We know that in the first few minutes after the Big Bang, the temperature dropped enough for nuclei to form. Protons and neutrons combined into the lightest atomic nuclei, hydrogen and helium, with traces of lithium. The amount of hydrogen and helium and lithium produced in those first few minutes matches, to high precision, what we observe in the universe today. This match, called Big Bang nucleosynthesis, is one of the strongest pieces of evidence for the hot Big Bang model. The numbers come out right. Earlier still, in the first second, the universe was so hot and so dense that the laws of physics we know begin to strain. The temperature was high enough that the four fundamental forces, gravity, electromagnetism, the strong nuclear force, the weak nuclear force, may have been unified into a single force, only to separate as the universe cooled. The earliest fraction of a second is, in 2024, still partly speculative. We have models, we have predictions, we do not have direct observations. The first 10 to the minus 34th of a second is by the conventional model, when the universe underwent inflation, a brief exponential expansion that stretched a tiny region of space into something much larger than the entire observable universe today. Inflation, proposed by Alan Guth in 1980 and refined by André Linde and others in the years following, explains several otherwise puzzling features of the cosmos, including the uniformity of the cosmic microwave background. But inflation itself is, in some details, still uncertain. Different versions of the theory predict slightly different things. We have not yet conclusively distinguished between them. And before inflation? Before the first fraction of a second? We do not know. Some researchers, like Roger Penrose, have proposed cyclic models in which our universe is one phase of a longer history. Others, like Stephen Hawking and James Hartle, have proposed that the question, what was before the Big Bang, may not have a meaningful answer. because time itself may not have existed in the form we recognize. Still others, working with quantum cosmology and string theory, have proposed that our universe is one of many in a vast multiverse. None of these proposals is currently testable in the way ordinary scientific claims are testable. They are at the boundary between physics and metaphysics. This is one of the places where we have to admit, plainly, we do not know. The universe before the cosmic microwave background is partly opaque to our observations. The universe before the first second is mostly opaque. The universe before the Big Bang itself, if there was such a before, is entirely opaque. There are walls in our knowledge. We have walked up to them. We have not crossed them. Whether we ever will is uncertain. But we have come close enough to the wall to see what is just on this side of it. And what is on this side of it is the cosmic microwave background, the wall of light from 380,000 years after the Big Bang. That is the deepest direct view we have. That is, in essence, the edge of the observable universe. So now ask the question that has been waiting all night. What does it mean to be at the edge? We have come along the spatial spine from your room to the cosmic horizon. We have passed every layer. We have measured every distance. We have named the structures and met some of their inhabitants. The horizon is now in sight. It is not a wall in space. It is a wall in time. Beyond it, things may exist, almost certainly do exist. But the photons from those things have not yet reached us, and as the expansion accelerates, more and more of them never will. What if the light that built the cosmic microwave background is itself only one face of a much larger object? What if the universe, the actual universe, is enormously larger than the part we can see? Perhaps infinitely larger, perhaps containing an unbounded number of regions like our own, each with its own cosmic horizon, each populated by observers who would describe their patch as the universe, because no other patch is visible to them. What if every conceivable arrangement of matter exists somewhere out there, beyond the limit of our sight? What if there are other observers in other patches looking at their own cosmic microwave backgrounds, never able to know about us, just as we are unable to know about them? What does it mean to live inside a horizon? What does it mean to know that your knowledge has a fundamental geometric limit? What does it mean that the universe is, by its own structure, divided into regions that cannot communicate? What does it mean that the most distant thing we can ever see, in principle, is not a star or a galaxy, but a wall of leftover heat? What does it mean that beyond that wall, in a region we will never reach, there are presumably other walls of heat, other observers, other histories? What does it mean to be one of an unimaginable number of vantage points on the same vast uniform fabric? A fabric that is, at its largest scale, not a fabric of stars and galaxies at all, but a fabric of horizons. We cannot know what lies beyond the horizon, not in principle, not by any conceivable instrument. The deadline of light makes sure of it. We can deduce, we can extrapolate, we can apply the cosmological principle and say that beyond the horizon, more of the same kind of universe presumably continues. But we cannot see. We cannot test. We cannot know in the strong sense of the word. The universe we have access to is a finite bubble carved out of an unknown larger reality by the speed of light and the age of time. Everything else is and will remain beyond our grasp. This is the paradigm shift the entire journey has been pointing toward. The universe is not the room. The universe is what fits inside the room. where the size of the room is set by how long light has had to travel since the beginning. The universe, as we mean the term in cosmology, is a horizon. It is a thing defined as much by what we cannot see as by what we can. Half of cosmology is a careful inventory of what is on this side of the wall. The other half is an honest acknowledgement of what is not, of what cannot be. And it gets stranger still, because the wall is not even stationary. It is shrinking, or rather, the universe inside the wall is being thinned out. Galaxies are being carried away. The cosmic microwave background is being redshifted into longer and longer wavelengths, becoming dimmer and dimmer, eventually becoming so faint that no instrument we can imagine could detect it. We are, right now, in the most informationally rich era the cosmos will ever have. Future observers will see less, far less. Eventually, in 100 billion years or more, an observer in our position will see only a single dark elliptical galaxy where the local group used to be, and beyond it, nothing. No galaxies, no microwave background, no evidence of expansion. The universe, to them, will appear static, eternal, and tiny. They will not be able to deduce the truth. The data will not be there. We are, in a sense, at the only window in cosmic history through which the full structure of the cosmos is legible. After us, the window closes. Stay with that for a while. Let it settle. The window closes. We are inside the only era when the universe's whole story can be read from the inside. And even now, even at this brightest moment, half the story is hidden behind a horizon we cannot cross. Picture yourself for a moment on a hilltop on a clear, dark night. Not in any specific place, just a hilltop. The grass is cool against your hand. The wind is light. There are no clouds. The sky is full of stars. You can see, with your own eyes, perhaps a few thousand of them. You can see the band of the Milky Way stretched across the sky. You can see, if you know where to look, the faint smudge of the Andromeda Galaxy. You can see, if conditions are right, the Magellanic Clouds, two small companion galaxies of our own. That is essentially the limit of your unaided vision. A few thousand stars, all within a few hundred light years of where you are sitting. A handful of nearby galaxies. The thin disk of our own galaxy is seen edge on. Nothing else. That is the universe as it appears to a human standing on a hill. That is what every human being, for almost the entire history of our species, has seen when they looked up. The full breadth of cosmic structure, the trillions of galaxies, the cosmic web, the horizon, the dark energy, the deadline. None of it is visible from a hilltop. None of it has ever been visible from a hilltop. And yet it is all there. It has always been there. The hill is sitting inside the same vast geometry. The grass under your hand is, ultimately, made of atoms forged in stars whose light is still traveling. The sky above you is full of structure your eyes cannot resolve. Stay on the hill. Do not move from it for a while. Notice your breath. Notice the cool air entering your lungs and warming and leaving again. Notice the faint pressure of your body against the ground. The earth is supporting you. The earth is also moving. It is rotating beneath you at hundreds of meters per second, depending on your latitude. It is orbiting the sun at 30 kilometers per second. The sun is orbiting the galactic center at about 220 kilometers per second. The galaxy is moving toward Andromeda at over 100 kilometers per second. The local group is drifting through Laniakea toward the Great Attractor at hundreds of kilometers per second more. And the entire fabric of space is expanding underneath all of these motions, carrying the most distant galaxies away faster than light. You are riding inside all of these motions at once. you feel none of them. The hill feels still. The night feels quiet. The ground feels solid. But the silence and the stillness are illusions of your own scale. You are, at this moment, moving through the universe at speeds that, if you could feel them, would terrify you. The reason you do not feel them is that everything around you is moving with you. The hill, the air, the trees, the planet, all riding the same currents. Motion is invisible when the whole environment moves together. That is one of the deepest insights Galileo gave us 400 years ago. We do not feel the motion of the Earth because we are part of it. So you sit on the hill, calmly, quietly, while everything around you flies through space. This is a good place to remember what we know, the provisions you packed at the beginning of the journey, the speed of light, the slowest courier in the universe, redshift, the stretching of light by the stretching of space, the cosmic horizon, the wall in time beyond which nothing can reach us. Carry them out of the journey too, when you carry the journey out. The hill is also a good place to think about smallness, not the smallness of being unimportant. That is a different kind of smallness, and we will discuss it shortly. The smallness of being a single point of view in an enormous space. From the hill, every direction stretches outward into more and more layers. Above you, the air, the moon, the planets, the stars, the galaxies, the web, the horizon. Below you, the rock, the mantle, the core, the molten heart of a planet that is itself a small body in a vast field of similar bodies. To your left and right, the curvature of the Earth, the slow turning of the surface, the continent you are sitting on, the ocean beyond it, the other continents, the other side of the world. Everywhere you look, the universe extends. There is no place where it stops. There is only the place where you can no longer see. There is a strange comfort in that. The fact that the universe extends in every direction means that you are not at an edge. You are not at a boundary. The horizon recedes as you turn. There is no wall against which you must press. The universe simply continues. You are inside it in the way a fish is inside the ocean, with no clear sense of where the ocean ends. Because for the fish, the ocean does not end in any direction it can swim. The fish, however, can imagine an edge. The fish can imagine a shore. Humans are like the fish in this regard. We imagine the universe must have an edge, because every other thing we know has an edge. Houses have walls, continents have coastlines, planets have surfaces, rooms have ceilings. Even our minds, in some sense, feel like they have edges. So we project that intuition onto the cosmos. We expect a wall. We expect a coastline. We expect a surface. The universe declines to provide one. What it provides instead is a horizon, a wall of time, not space, a boundary defined by the speed of light and the age of the cosmos, not by the geometry of any structure. Beyond the horizon, more universe presumably continues. But we cannot see it. The horizon recedes as the universe ages, in some sense. Light from farther and farther away has had time to reach us, and so the visible patch grows. But the horizon also closes. In another sense, galaxies near the edge are being carried away faster than their light can travel, and so they cross out of view. The two effects compete. For a long time, the first dominated. The visible universe was getting bigger. Now, with dark energy in command, the second is beginning to dominate. The visible universe is, very slowly, beginning to thin out. We are at the turning point, or just past it, the brightest moment of cosmic history. the window of maximum legibility. Stay on the hill a while longer. The night is long. The air is cool. There is no rush. The universe is not going anywhere immediately. The horizon will not collapse tonight. The galaxies will not vanish before morning. We have time. Time for us on the human scale. The universe is patient. It is willing to wait while we look up at it. There is a thought worth lingering on here before we make the final approach to the existential climax of the journey. The fact that the universe contains observers like us, animals that can look up, that can wonder, that can build telescopes and measure the cosmic microwave background and deduce the age of the cosmos to within a fraction of a percent, is itself one of the most remarkable features of the universe. We are not separate from the cosmos. We are a feature of it. Whatever the universe is, it is the kind of thing that produces beings who can ask what it is. The hydrogen that came out of the Big Bang was, in the end, capable of organizing itself into Carl Sagan, into Henrietta Leavitt, into Edwin Hubble, into the hands and eyes of the engineers who built the Planck satellite. The universe is, in some sense, looking at itself through every set of eyes. That is not a mystical claim. It is a structural one. The matter that makes up your body has been continuous with the rest of the universe since the beginning. Every atom in you was either created in the first few minutes after the Big Bang, or in the core of a star that lived and died long before the sun was born. The lineage is unbroken. You are not a visitor in the universe. You are not a foreign object placed into it. You are a configuration of the same matter that fills the cosmic web, organized for a brief time into a pattern that can think and feel and ask questions about its own origin. When you look up at the stars, you are looking at relatives, distant, unrecognizable, made of the same elements, formed by the same processes. The stars do not look back, but you are made of their ancestors, and they are made of yours. The universe is one extended family of matter, organized in different ways at different scales. Some of the matter has become stars, some have become galaxies, some have become you. The arrangements differ, the substance is shared. Hold that on the hill for as long as you can. We have one more layer of meaning to sit with before we approach the existential climax: the strangeness of the act of measurement itself. When you measure the distance to a galaxy, you are doing something almost philosophically reckless. You are taking a small handful of photons that arrived at your telescope after traveling for 1 billion years across an expanding universe. You are decoding the redshift in those photons. You are comparing them with a model of how the universe expands, and you are deriving from this thin streak of arriving light the present-day distance to a place that is more than 30 billion light-years away. The chain of inference is long. There are many assumptions. The number you produce is, against all reasonable expectations, accurate. We can check it in many ways. The cosmic distance ladder, the cosmic microwave background, the rate of expansion, the abundance of light elements, the formation of large-scale structure. All of these independent lines of evidence converge on the same numbers. The universe does not tell us its size. The universe tells us its photons. From those photons, we deduce its size. This deduction is one of the great achievements of the human mind. It is not a guess. It is the result of more than a century of careful, painstaking, often frustrating work by thousands of researchers across many countries. Hubble, working at Mount Wilson in California in the 1920s, with a telescope that today would be considered modest, established that the universe was much larger than the Milky Way and that it was expanding. Lemaitre, a Belgian priest and physicist, working at roughly the same time, derived the equations that describe that expansion and proposed what we now call the Big Bang model, though the term itself was coined later, sarcastically, by the astronomer Fred Hoyle. Penzias and Wilson, working at Bell Labs in 1965, found the leftover heat. The COBE, WMAP, and Planck teams, working from the 1990s through the 2010s, mapped that heat in extraordinary detail. The Supernova Cosmology Project and the High Z Supernova Search Team in the late 1990s found the acceleration. The Gaia satellite, throughout the 2010s and 2020s, mapped the local stars with unprecedented precision. The James Webb, beginning in 2022, has been pushing the visible horizon back into the cosmic dawn. The picture we have is a collective creation. No one person built it. No one nation built it. The full understanding of the cosmos as it stands today is a structure built by many hands, often working independently, often correcting each other, sometimes competing, sometimes collaborating. And the structure that has emerged is, against all odds, internally consistent and externally testable. The universe has cooperated. The data have come back the way the theory predicted, again and again, with surprises along the way that sharpened the picture rather than destroying it. This is one of the most extraordinary things about being human at this moment. We can know all of this. Our species can, collectively, hold an accurate map of the cosmos in its libraries and databases and instruments. We can hand that map to a child. The child can read it. The child can learn that the universe is 46 billion light-years across, that there are 2 trillion galaxies, that the cosmic microwave background is the leftover light of an early hot phase, that dark energy is accelerating the expansion. The child can absorb, in an afternoon, more about the structure of the cosmos than the entire human species knew 150 years ago. That is a gift we have given each other. The map, the picture, the understanding. It is also, perhaps, a curse. Because once you know what is out there, you cannot unknow it. Once you understand the scale, you cannot return to imagining a small, cozy universe with a comfortable wall around it. The grandeur is not optional. The horizon is not optional. The deadline is not optional. We have looked at the universe, and the universe is what it is. We have to live in the room as it actually is, not as we wish it were. What does that mean for us? What does it mean to be a creature on a small blue planet, in a small solar system, on the outskirts of a medium-sized galaxy, in a small local group, in a corner of a supercluster, in one of 2 trillion galaxies, inside a horizon that is 46 billion light-years deep, in a universe whose expansion is accelerating, whose matter is mostly invisible, whose largest structures are filaments of galaxies that we are too small to perceive, whose age is 14 billion years, whose future is a long thinning out, whose beginning we cannot see beyond the wall of light. What does it mean to know all of this, and to still go to work in the morning, to still cook dinner, to still hold the hand of someone you love, to still mourn the dead, to still hope? It means, at minimum, that the human story has been radically resized. Every previous generation imagined itself at the center of something. The medieval cosmos placed Earth at the center of the heavens. The Enlightenment cosmos placed humanity at the apex of nature. The industrial cosmos placed our civilization at the head of progress. We placed ourselves again and again at the front of a story. The cosmos has politely declined to confirm any of these placings. We are not at the center of space. We are not at the center of time. We are, as far as anyone can determine, one species among many, on one planet among possibly trillions. in one galaxy among 2 trillion, in one observable patch among presumably an unbounded number, in an arrangement of matter that is itself one possible configuration among many. There is nothing in the data that says we are special. There is also nothing in the data that says we are not. The cosmos does not deliver verdicts on importance, it delivers structure. What we make of the structure is, in the end, up to us. There is a thread, an old thread, running through human history that goes back at least as far as ancient Mesopotamia, when the first astronomers carved star charts into clay tablets in the temples of Babylon. They watched the night sky with patience. They mapped the motions of the planets. They named the constellations. They believed, often, that the heavens directly shaped human affairs, that the gods communicated through the stars, that the stars governed the fates of kings. That belief has faded. The heavens, we now know, do not communicate through the stars. The stars are physical objects, ruled by physical laws, indifferent to human affairs. They are not messengers. They are simply themselves. And yet, the impulse that drove those Babylonian astronomers was the same impulse that drives the astronomers of today. Looking up, the careful watching, the need to understand the pattern. The Sumerians, the Egyptians, the Greeks, the Persians, the Chinese, the Mayans, the Indians, the Arabs of the medieval world, the Europeans of the Renaissance. Every literate culture in the history of the species has, at some point, devoted serious effort to understanding the sky. The instruments have changed. The questions have not. When Aristarchus of Samos, in the 3rd century BCE, first proposed that the Earth orbited the Sun, he was working from logical inference and limited observation. His proposal was rejected for almost 2,000 years, until Copernicus revived it in the 16th century. When Galileo, in 1610, pointed a small telescope at Jupiter and saw 4 moons orbiting around it, he disproved the assumption that everything in the heavens orbited the Earth. When Isaac Newton, in the 1680s, formulated his laws of gravity, he showed that the same force that pulled an apple from a tree pulled the moon around the Earth and the Earth around the Sun. The heavens and the ground became, for the first time, a single system. When Einstein, in 1915, showed that gravity is the curvature of space-time, he made it possible to think about the universe as a whole, as an evolving geometric object. When Hubble, in 1929, showed that the universe was expanding, he turned cosmology into a historical science, a science of the past. When Penzias and Wilson, in 1965, heard the leftover heat of the Big Bang in their antenna, they confirmed the historical science with the deepest evidence yet. This is the line we are part of. This long, multi-millennial line of looking up. The line of asking what the lights are. The line of refusing to accept the easy answer. The line that has carried us, over thousands of years, from clay tablets in Babylon to the Planck satellite at the second Lagrange point. The line is not finished. It will continue. James Webb is reading the cosmic dawn. The next generation of telescopes, the Vera Rubin Observatory, the Square Kilometre Array, the Roman Space Telescope, the Extremely Large Telescope, the proposed gravitational wave observatories of the next decades, will continue the work. The picture will deepen. The horizon will be examined more closely. The mystery of dark energy will be probed. The earliest galaxies will be studied in finer detail. The line continues. But the line will eventually end. Either because we end as a species, or because the cosmos runs out of legible information for us to read. Or both. The window closes. Future cosmologists, far enough in the future, will not have access to what we have access to. And we ourselves, even in our brief privileged moment, cannot see beyond the cosmic horizon, cannot see before the Big Bang, cannot see what dark matter is, cannot see what dark energy is in any deep sense. There are walls we have not crossed. There may be walls we cannot cross. What does it mean to live with walls in your knowledge? The honest answer is that humans have always lived with such walls. Every generation has known some things and not others. Every generation has had its own horizons, its own walls of light. The horizon of a Babylonian astronomer was a few thousand stars and a handful of planets. The horizon of a Renaissance astronomer was a slightly more refined version of the same, plus some moons of Jupiter. The horizon of a 20th century astronomer was the observable universe and the cosmic microwave background. Our horizon, in 2024, includes all of those plus the early galaxies of the cosmic dawn and the first images of black holes. The horizon has expanded. It is still bounded. To live with bounded knowledge is the fundamental human condition. The cosmos has, in this sense, only confirmed something that was always true. We do not have access to everything. We never will. We have to make our peace with knowing partially, with measuring carefully, with extrapolating cautiously, with admitting freely what we do not yet know. The Babylonian who carved the first star chart did not know about quasars or dark matter or the cosmic microwave background. We do not know what the Babylonians' descendants, 4,000 years from now, will know that we do not. The line continues. The map deepens. Each generation contributes a few more pixels to a picture that will never be finished. This is a noble inheritance. To be a small contributor to a multi-millennial project of looking up. To know that the picture you helped build will be improved by people who do not yet exist. To accept that the work will continue without you. To do the work anyway because looking is its own reward. There is something deeply human about this. The willingness to participate in something larger than oneself. Knowing that one will not see its completion. Knowing that the completion may not even be possible. Knowing only that the work is good, that the looking is good, that the careful, patient mapping of the actual world is one of the things we are for. If our species has a calling, beyond the obvious calling of survival and care for one another, it may be this: to look up, to pay attention, to map, to measure, to pass the map on. We have come a long way on this hill. The night has deepened. The stars have moved a little with the rotation of the Earth. The constellations that were rising in the east have climbed higher. The constellations that were overhead have begun to drift west. Time is passing, even on a quiet hill on a quiet night, and the universe is continuing to expand, and the horizon is continuing to recede, and the deadline is continuing to write itself. It is almost time to get up, almost time to let the journey reach its final pivot. The hill has been kind. It has held us. It has let us breathe. It has given us a place to think. Soon we will have to face the largest question of all. The question that hangs at the end of every cosmological journey. The question that does not have a comfortable answer. The question that humans have been asking in different forms for as long as they have looked up. What does it mean that all of this exists and that we are inside it briefly? We will face that question now. Stand up from the hill. Take one slow breath. The night is still cool. The ground is still beneath your feet. The sky is still above your head. The journey is almost complete. There is one final layer to pass through. The universe began in a hot, dense, smooth state about 13.8 billion years ago. From that beginning, it expanded and cooled. allowed atoms to form, allowed light to escape, allowed gas to clump under gravity, allowed stars to ignite, allowed galaxies to grow, allowed planets to form, allowed chemistry to develop, allowed the first molecules of life to organize themselves on the surfaces of a few damp worlds, allowed those molecules to evolve, allowed the evolution to produce eyes, allowed the eyes to look up. From the beginning to the eye took 13.8 billion years. The eye is, in this sense, the universe's slowest accomplishment. The cosmos worked patiently for over 13 billion years to produce something that could see it. Now consider what has happened. A configuration of matter on a small planet, in a small solar system, in a moderate galaxy, in one of trillions of galaxies, has assembled itself into a creature that can think about the structure of the entire cosmos. That creature can measure the cosmic microwave background. That creature can chart the cosmic web. That creature can know that the expansion is accelerating, and that the horizon is closing, and that the window is brief, and that the picture, even now, is incomplete. That creature is you, sitting on a hill or in a room or wherever you happen to be tonight. The cosmos has produced an organ capable of looking back at it, and that organ is, for this moment, yours. The temptation, when one realizes this, is to feel small, to feel insignificant, to feel that one is merely a flicker against an enormous backdrop, a brief candle in an indifferent dark. That is one possible response. It is a common response. It is not the only response. The other response is to recognize that the flicker is the universe's own light. The candle is not separate from the room. The candle is the room, briefly organized into something that can burn. The cosmos, in producing you, has produced one of its own modes of self-awareness. You are, for a moment, the universe looking at itself. This is not poetic exaggeration. It is a simple consequence of the fact that you are made of the same matter as the cosmos, that your atoms came from stars, that your eyes evolved through cosmic processes, that your mind is the result of physical patterns within physical matter, and that those patterns are, themselves, products of the same universe they perceive. The looker and the looked at are not separate substances. They are the same substance, organized in two different ways. One way is a galaxy. Another way is a person on a hill, watching a galaxy. Both arrangements are made of the same atoms. Both follow the same laws. Both will last only for a while. Both are temporary patterns in a continuous fabric. The galaxy will, in time, dissolve. The person will, in less time, dissolve. The fabric will continue. New patterns will form. Some of them will perhaps also be capable of looking up. The universe contains many such patterns. We do not know how many. We do not know how many planets harbor minds. We do not know how often in the long history of the cosmos the conditions for awareness arise. But the conditions are not impossible. They have arisen, at minimum, here. Whether they have arisen elsewhere is, in 2024, an open question. The Drake equation, formulated by Frank Drake in 1961, attempts to estimate the number of communicating civilizations in our galaxy. The estimates range from 1 to many millions. We do not know. We have not yet found another. We have also not yet looked very hard on cosmic scales. But even if we are alone in the galaxy, even if we are alone in the local group, even if we are the only minds in the entire visible universe, the fact that there is at least one mind looking out at the cosmos is itself extraordinary. The universe has, by producing us, become a thing that contains awareness of itself. That awareness may be tiny. That awareness may be brief. That awareness may not even be the most important feature of the cosmos, but it is real, and it is here, And right now, at this moment, you are exercising it. The journey to the edge of the universe is, in this sense, also a journey to the edge of yourself. The cosmic horizon is the limit of your sight. The deadline of light is the limit of your knowledge. Beyond these limits, you cannot go. But within these limits, you have access to a structure of unimaginable size and complexity, organized in ways we are still only beginning to understand, populated by stars and planets and galaxies and forces and processes that have been unfolding for over 13 billion years. And the entire arrangement is, for this brief moment, available to your attention. That is the gift. That is the privilege of being awake, on this planet, at this time, with the eyes you have, looking up. It will not last forever. Your eyes will not last forever. The window of cosmic legibility will not last forever. But for now, the window is open. The eyes are open. The universe is visible. Looking is possible. The journey to the edge of the universe ends, in a sense, exactly where it began. On the hill, in the room, with your breath, with the slow rise and fall of your chest, with the quiet awareness that the cosmos extends in every direction, that it has always extended, that it will continue to extend long after you are gone, and that for this brief moment, you are part of it. Not a visitor, not a stranger, part of it. The hill has held you. The night has held you. The atoms in your body, ancient and recycled, have held you together for the duration of one human life, and they will, when that life is over, return to the larger fabric. You are borrowed material, briefly arranged. The arrangement will end. The material will continue. The cosmos, in the long run, is conserved. So, here is the picture, gathered together, before we let the night settle over us for the last time. We began in your room, with the air in your lungs and the breath against your skin. We measured the thinness of the atmosphere, that 100-kilometer shell of breathable sky above the surface, the only environment our species has ever lived in. We climbed past low Earth orbit, where a few hundred people in the entire human story have ever traveled, and past the moon, where 12 sets of footprints stand undisturbed in the dust, the deepest extension of our species into space. We crossed the inner solar system, past the rocky planets and the asteroid belt, past Jupiter and Saturn and the ice giants, past the heliopause, where the Voyagers drift outward in the slow walk of half a century, broadcasting faintly back to a world they can no longer see. We crossed the long darkness between stars, 4 light years to the next sun, hundreds of light years to the edge of the local bubble, 26,000 light years to the heart of our galaxy, where Sagittarius A star, the 4 million solar mass black hole at the center of the Milky Way, anchors 100 billion stars in slow rotation. We pulled back from the galaxy and saw it as one disk among many. 2.5 million light years to Andromeda, the next great spiral, falling toward us at over 100 kilometers per second, on course for a merger we will not be alive to see. 10 million light years across the local group, 500 million across Laniakea, our home supercluster. And then the cosmic web, with its filaments and its voids, with the Boötes void 300 million light years across, with the cosmic structure resolving itself at the largest scales into a smooth, uniform fabric without a center, without a privileged direction, without an edge of the kind our intuition expects. We met the cosmic microwave background, the wall of light from 380,000 years after the Big Bang, the deepest direct view we have. We met dark matter, which holds the galaxies together but cannot be seen. We met dark energy, which is pulling everything apart, which sets the deadline. We met the early galaxies of the cosmic dawn, seen by the James Webb Space Telescope as they were just a few 100 million years after the beginning, their light stretched into infrared by the long expansion of space. And we came to the edge, 46.5 billion light years from where you are sitting. Not a wall, not a coastline, a horizon, a boundary in time set by the speed of light and the age of the cosmos. Beyond it, more universe almost certainly continues. We will never see it. The deadline of light makes sure of that. This is the room we live in. The room is enormous. The room is 13.8 billion years old. The room is, on the largest scale we can measure, smooth and uniform, the same in every direction, with no preferred place. We are inside it, briefly, on a small blue planet, in a small solar system, in a medium-sized galaxy, in a corner of one supercluster, on one strand of the cosmic web. We are not at the center. There is no center. We are, like every other observer in the cosmos, at our own apparent middle, looking out at a sphere of receding light, watching the universe's history unfold across the line of sight. What do you do with this picture? That is, in the end, the only question that matters. The picture is a fact. The numbers are real. The structure is real. The horizon is real. The deadline is real. None of it can be unknown. So what do you do with it? You can be afraid. The scale is, in a real sense, frightening. The smallness of any individual life against this backdrop can feel unbearable. The brevity of any human moment against 13.8 billion years can feel cruel. You can be indifferent. Many people are. The cosmic scale is, for most practical purposes, irrelevant to whether the rent gets paid or whether dinner is ready. Most of life happens at the scale of meters and minutes, not light years and eons. You can be in awe. The fact that any of this exists at all, that the universe is something rather than nothing, that the matter has organized itself into stars and galaxies and bodies and minds, that you can know about it, is in itself astonishing. Awe is a reasonable response. You can be quiet. You can sit with the picture without forcing a verdict from it. You can let the cosmos be what it is, and let yourself be what you are, and not require either to give the other a justification. There is no correct response. The cosmos does not demand one. The cosmos simply continues. The expansion accelerates. The galaxies recede. The atoms in your body keep doing what atoms do. The story goes on, with you in it for as long as you are in it, and without you when you are not. If something in this journey changed how you think about the place you live in, then the time was well spent. You will go to sleep soon on the planet you started on. You will wake up to a sky that looks the same as it always has. The sun will rise, the day will begin. The grocery list will need to be made. The dishes will need to be washed. The work will need to be done. None of the cosmic scale will visibly intrude. The hill will still feel like a hill. The room will still feel like a room. But somewhere, in the back of your mind, the picture will be there. The 46 billion light years, the 2 trillion galaxies, the cosmic web, the horizon, the deadline, the slow walk of the Voyagers, the 12 footprints on the moon, the breath in your lungs, made of molecules older than your species, the atoms in your fingertips, forged in stars that have been dead for billions of years, the continuous fabric of matter, of which you are one brief, organized configuration, capable for a little while of looking up. That picture, once you have it, does not leave. It changes the way the night feels. It changes the way the morning feels. It changes the weight of what is local and what is far. It changes nothing about the practical demands of living. It changes everything about the meaning of them. The journey ends here, on a planet, in a room, with your breath. The cosmos extends outward in every direction, as it has always extended, as it always will. You are inside it. You are part of it. You are the universe, briefly arranged into a being that can know. The matter in your body will, one day, return to the fabric. New patterns will form from it. Some of them, perhaps, will also look up. Some of them, perhaps, will also wonder what is out there. They will measure. They will map. They will deduce. They will arrive by their own paths at some version of the picture you now carry. The line will continue. The line is older than any of us. It began, in some sense, with the first eye that opened on Earth and registered light. It continued with the first mind that watched the stars move and tried to understand the pattern. It runs through Babylon, through Alexandria, through the medieval observatories of Persia and India, through Florence and Cambridge and Pasadena, through the radio antennas of New Jersey and the satellites at the second Lagrange point, through every laboratory and library where someone has tried to understand the cosmos. The line is multimillennial. The line is collective. The line will continue after every individual on it is gone. You are part of that line tonight. By looking up, by listening to this, by holding the picture in your mind for the length of a single long evening, you have participated. You have added your attention to the inheritance. You have done what humans do. That is enough. That is more than enough. Now let the night return. Let the air settle around you. Let your breathing slow. The picture will keep in the back of your mind until morning. The cosmos is in no hurry. The horizon is in no hurry. The atoms in your body are in no hurry. They have been together for the length of one life so far, and they will be together for the rest of it. And after that, they will be elsewhere, doing something else, somewhere in the same vast fabric. Thank you for traveling with me tonight. Thank you for sitting on the hill. Thank you for breathing through the long descent through layers of distance, from your room outward to the edge of the visible. Thank you for staying with the numbers when they grew too large to feel, and for letting your body anchor what your mind could not quite grasp. Thank you for being here, awake, briefly, on this small blue planet, in this small solar system, in this corner of the cosmic web, in this brightest moment of the universe's legibility, when the picture is still for a while available to be read. The journey to the edge of the universe ends as it began, with a breath. Take one in, let it out. The room is around you. The planet is beneath you. The cosmos is above you in every direction, extending farther than you can see. The horizon is real, and the deadline is real, and the picture is real, and so are you. Sleep well.